Hello all, good morning. This is Dr. S. Subalakshmi, an assistant professor in the Department of Mathematics, SNS College of Technology. This is a lecture video series on the course Probability and Statistics, and now we are looking on to the content of statistics. Here we are going to see the testing of hypothesis, under which we are going to see the chi-square test. Chi-square test comes under two categories, which is goodness of fit and independence of attributes. In the previous lecture video, we have seen the problems regarding goodness of fit. Its formula has been explained earlier. Its chi-square value, calculated value, is approximately equal to the summation of observed frequency minus expected frequency the whole square divided by the expected frequency. O is the observed frequency and E is the expected frequency. And the degrees of freedom rho is equal to n minus 1. This is what we have learnt in the as a formula. Now we will look on to the properties of the chi-square test. The mean of chi-squared is equal to the number of degrees of freedom, which means the average of the chi-squared test or the chi-squared values is always equal to the degrees of freedom. Degrees of freedom is nothing but the rho value, which is n minus 1. And the second thing is the variance of chi-square distribution is twice the degrees of freedom, and also we can note that variance is equal to the 2 times of the degrees of freedom. Third property is a chi-squared is a chi-squared variate which rho degrees of freedom, then chi-squared by 2 is a gamma variate with parameter rho by 2, which means what we can say is if it is a chi-squared variate we will treat as rho, and if it is a gamma variate we will treat as rho by 2. In the fourth property, the standard chi-square variate tends to standard normal variate as n tends to infinity. In the chi-square distribution, if we take if we get as n tends to infinity, which means n is infinitely large, we can say that the chi-square will change to a normal variable. Now we will have some of the applications of chi-square test. To test if the hypothetical value of the population variance is equal to the given variance, which means that there is no difference between the two observed frequency and the expected frequency. Those type of things can be checked using the chi-square test. Second is to test the goodness of it. How come the fitness is good enough to meet the standard specifications is checked. Second one is third one is to test the independence of attributes. Independence of attributes is nothing but the attributes or the specifications or the properties or the behavior of the content or the data given is checked or analyzed or verified using the given data and using the standardized value of chi-square, and we will be giving a conclusion. Those type of independence is also noted. And finally, to test the homogeneity of independent estimates of the population variance is also noted. Homogeneity means how come all the given attributes are coming under the same property or behaving under the same character. We will be noting it and we will be saying a conclusion with the help of chi-square test. This is what we do in chi-square test, and we will move on to a problem regarding goodness of fit, which we have already seen in the lecture video. This is a problem on the number of accidents on a weekly basis, aircraft accidents on a weekly basis. You are given with the data for all the weekdays for Monday to Saturday, and the number of accidents per day is also given here. As we can note, it is also it is given here. So what we are asked to test is to test whether the accidents are uniformly distributed over the week, which means this uniformly is a key point to note. That it comes under the chi-square test. So how to start with the problem? You have to write for the given data. What is the given data? Total number of accidents, which is equal to 84, as we can just sum up from the table here. We can just sum it up and we will have the value to be 84, and the number of days given is 6, and therefore the expected frequency E to be calculated as 84 by 6, which is 14. And now we will move on to the actual testing procedure now. What is our testing procedure? This is our first procedure. Step 1 is using null hypothesis. What is null hypothesis? H naught. It is denoted by H naught. The accidents are uniformly distributed. What is alternative hypothesis? H1. So accidents are not uniformly distributed. Are uniformly distributed or not uniformly distributed. This is what our null and alternative hypothesis goes with. This is the actual procedure for testing. Now with the step 3 is nothing but the level of significance. What is level of significance? It is the significant level under which we can accept the given lot, or under which we can take up the given data on hand. Level of significance is 5%. Since it is not given in the question, we will be mentioning it as 5%. Now we have to calculate the value for chi-square, which is chi-square calculated, which is summation of observed frequency minus expected frequency the whole square divided by E. So for which we will be having this table, and under which we have found the value to be 2.148. And later the degrees of freedom is also given here. What is this eta? A rho is equal to n minus 1, and therefore which is 5. So as per the standardized table of chi-square distribution, we have got the level of significance to be 5%, and for 5 degrees of freedom the tabulated value is 11.07. So with this in hand, what we have to do, we have to compare the calculated value and the tabulated value. As we can see, it is much lesser than the calculated value is much lesser than the tabulated value, and therefore what we can opt from this is we can just accept the hypothesis which is our null hypothesis, and therefore what we can conclude is we can conclude that the accidents are uniformly distributed over the week. So this is how we perform a chi-square test under the given data. So we will have some more videos on goodness of fit and independence of attributes in the next videos as well. Thank you.